All right, now we're going to talk about the second part of section 8.4, graphing other types of rational functions. We looked at functions and transformations in the form a over x minus h plus k. This video in the second half of 8.4 deals with other types, which you'll see in a second. But first of all, if you need to pause the video, please do to copy this down. But we need to make a distinction between two types of functions. One is a discontinuous function. What we're studying here with rational functions in Unit 8, they are all discontinuous because it is a function whose graph has one or more holes, gaps, or breaks in it. The one I circled is what we're dealing with. Obviously, there's a gap or a break. The graph doesn't go on forever. I can't keep tracing it with a pencil without lifting it one time. I can trace it like this, but then I have to lift it up and get it to go over here, and that would be a break. The last two examples are what you're going to get in pre-calc. This example right here in the box is an example of a function that has a hole in it. That hole is right there. I can't keep drawing this line without lifting my pencil and then moving it to the other side. And the same with this one that I underlined in green. That's another example. This is actually called a piecewise function, something that you will see in pre-calc. A continuous function is all those other functions that we've already studied this year, linear, quadratic, etc. That's a graph who does not have any gaps or breaks in it. Those are the ones you're familiar with. But discontinuous summarizes this particular unit. All right, next notes. We're going to talk about graphing other rational functions. Those are the ones that are not in the form in green. I talked to you about those in a prior video. We're going to talk about things like what's in the green box now. Because this is a rational function. This is rational. And the reason it's rational is because it has an x in the denominator. Okay? So, there's some rules that you have to write down. So please pause the video and copy it down as I explain it. If you have a function in the form p of x divided by q of x, where p and q are polynomials, obviously in this example, the top would be called p of x. That's a polynomial. The bottom is also a polynomial. We're just going to call that q of x. The top is always p. The bottom is always q. And it's in reduced form. The function in my box is in reduced form because if I factor the numerator, that would be x minus 3 times x plus 1, and that does not reduce with anything in the denominator. It's got to be in reduced form. If so, a couple things that you know are true. The graph will have zeros where the numerator, the polynomial, is equal to 0. Okay? We'll talk about this in the next video. I'll do this example right here in the next video. And number two, the graph, this graph right here, will have a vertical asymptote where the denominator is equal to 0. So obviously our denominator is going to be equal to 0 when x is 2, so that will be our vertical asymptote. Okay, so if you need to pause the video, please do, because I have one more page of notes that we need to talk about. All right, big screen of notes here. You can pause it and write it down and then start it again when you're ready. This screen talks about where the horizontal asymptotes are. The existence and location, whether or not they exist and where they are, depends on the degree of the polynomials in the numerator and denominator. All right, in the prior screen I talked about being in the form p of x divided by q of x. So here's your rules. If p of x divided by q of x are polynomials that are in reduced form, then what do you know? Well, first of all, you know for sure that the graph has at most one horizontal asymptote. At most one. It could be 0, but it may have one. Now, where are they? Where are they? Well, where they are depends on the degrees of p and q. If the degree of polynomial p is greater than the degree of polynomial Q, it will have no horizontal asymptote. If the degree of P, can't erase it, so sorry, we're just going to have to leave that. If the degree of P is less than the degree of Q, then the line y equals 0 will be your horizontal asymptote. Again, if the degree of P is less than the degree of Q. And finally, what if the degrees are equal? What if the top and bottom are the same? Then the horizontal asymptote will be the line y equals the lead coefficient of P divided by the lead coefficient of Q. Those are your rules. So again, please pause the video. That wraps up this video because I didn't want to make it too long. The next video, I will use those rules and do some examples for you. If you have questions, please ask during class.